Okay, so today we're going to start talking about polar and put some of the calculus concepts we know together with the polar topics we've been learning the last couple of days. So one skill that's really important when you're working with two polar curves is being able to figure out where they intersect. So I want you to think about these two curves. So we have the function r equals 1 and r equals 1 minus 2 cosine theta. Think back to the handout I gave you the other day. If you'll recall that r equals 1 is a circle centered at the origin with a radius of 1. And the other function there is a cardioid. And I'll show you a picture of this in a minute. But before I do that, I want to look at what happens if we were to just set these equal to each other. If we set them equal to each other, do a little algebra here. We're looking at where does cosine theta equals 0. And of course, if you think about your unit circle, we know that that happens at pi over 2 and 3 pi over 2. So if we're to plug in those pi over 2 and 3 pi over 2 values for theta, the points of intersection would just be 1 comma pi over 2 and 1 comma 3 pi over 2. But the thing you need to be careful of is, are these all the points of intersection? And that's where the graph comes in. You need to make a little sketch and see what's going on. Here's a picture of it. So r equals 1 with the circle, and the other one is the cardioid in red. You can see that there's another point of intersection. And the reason this occurs is if you think about the curves traveling. So think about the circle. The circle repeats every pi units. If you plugged in 0 for theta, you'd get a value of 1, pi over 2, you'd get a value of 1, etc. But then the cardioid hits at different times. So they're going to intersect at the origin, at this point here, but they're going to do so at different times. So the coordinates for this third point of intersection based on the graph, we'll just use the Cartesian coordinates, -1, comma 0. The main thing to remember is make a sketch of this. Check it with the algebra first, and then make a sketch to see if you've covered all your bases. One way to think of these points of intersection is to imagine if there were two satellites intersecting the Earth. So they won't collide as long as they reach those points of intersection at different times or different theta values. Let's do a little example here. Find the points of intersection of this function, or these two functions. So set them equal to each other. Solve algebraically first. We get 1 equals 2 cosine theta. Divide by 2. Where does cosine theta equal 1/2 on your unit circle? Of course, that would be at pi over 3 and 5 pi over 3. And if we make a sketch of this, we've got a circle. 3 cosine theta is a circle, symmetric over the x-axis. And the other function is a cardioid. Take a look. So you can see pi over 3 is in the first quadrant right here. That was the point of intersection for theta equals pi over 3. And the 5 pi over 3 is here. That was the other point of intersection. But they also intersect at the origin. So we need to consider that point of intersection at 0, 0. What's going on here is that the first equation, the cardioid, is hitting that origin with theta equals pi, but the second equation is hitting it with theta equals pi over 2. So that's why we didn't find the points algebraically. But make sure we include it by making the sketch. Okay, I want to talk for a second about area and how we look at area in terms of polar. So from trig, I want you to think about how we found arc length. So in trig, back in pre-calc, you would have learned a formula for arc length. S, or we called it arc length, was equal to r times theta. So r was the radius of the circle, and theta was how much of it swept out. So for example, if theta, let's say, were pi over 4 radians, so just this first little wedge right here, and let's say the radius was 4, pi over 4 times 4, this would be an arc length from there to there of pi units. If we wanted to find area contained inside of a polar curve, how could we do it? Well, if you'll recall last year when we first learned area, we thought about imagine drawing rectangles underneath the curve and adding up an infinite number of those rectangles, and that led us to the integral. Well, this time, instead of doing rectangles, we're going to think of this as triangles. We're going to think about breaking this up into small triangles. As theta increases from the x-axis out, the area is swept out in a circular pattern by these triangles, and we have an infinite number of them underneath this curve. So think about for a very small theta, or d theta, the curve could be approximated by a straight line, and the area could be found using the triangle formula. Let's look at a smaller picture of this. So let's imagine this is one of those triangles. R is the radius. Notice that R is the what for the triangle here? That's right, R is just the height of the triangle. The base is given by R times theta. That was our arc length formula, but if d theta is our very, very small part of theta, that arc length, that little piece of that triangle, that piece of the curve, is r d theta. So we have 1/2 base times height. Base is the r d theta, height is the r. So the area for this triangle, I'm going to call it dA, because it's a very, very small area, is 1/2 r d theta times r, or 1/2 r squared d theta. And so if you think about how many triangles are we talking about? We're talking about very, very small triangles. There's not a set number of them, so we're going to add it up to infinity. If we sum up the area of all those triangles to infinity, think about the integral here. The area in polar, it's a very important formula you're going to want to memorize. The area in polar is the integral from theta 1 to theta 2 of 1/2 r squared d theta. Let's do an example here. So suppose we're asked to find the area enclosed by this cardioid, and of course you could distribute that too if you like. I think it's helpful to make a sketch so you can kind of see what we're talking about here. And the graph here starts at theta equals 0. If you plug in 0 for theta, this will give you an r value of 4. So you can see that theta equals 0 would start out here. At theta pi over 2, you would be here on the y-axis. At theta equals pi, you'd be at the origin. At theta equals 3 pi over 2, you'd be at -2. Actually, this really shouldn't be negative because we're talking about polar, but that's okay. And then at 2 pi would be back here. So this sweeps out from 0 to 2 pi. But to do the integral, we're going to integrate from 0 to 2 pi of 1/2 r squared d theta. So let's replace r with the function. We have to FOIL this out. We're going to square it. Notice the 4 and the 1/2 just reduced to 2. I went ahead and distributed the 2 here. And notice I replaced cosine squared theta. Think back to chapter 8 when we were learning all those integration techniques. To integrate cosine squared, we replace it with the identity, 1 plus cosine 2 theta over 2. There it is again. There it is cleaned up just a little bit. And then if we integrate, go through, we get 3 theta plus 4 sine theta plus 1/2 sine 2 theta from 0 to 2 pi. Apply the fundamental theorem of calculus. We get an answer of 6 pi. Now, a lot of times with these graphs, you'll notice that there is symmetry. There's a lot of symmetry involved. For example, I'm going to go back to the picture for just a minute. We integrated this from 0 to 2 pi, but we could have just as easily integrated it from 0 to pi. That would have gotten us the top half of the curve and then doubled it. So sometimes if the numbers are easier, you might want to consider that. Okay, let's try another one. Find the area of one petal of the rose curve given by the function r equals 3 cosine 3 theta. We're going to sketch this. So here's a picture of the rose curve. If you look back at your handout that I gave you the other day, we had some information about rose curves. If the n in front of the theta was odd, that's how many petals we have. So to figure out the solutions to this equation, we want to know where this will hit the pole. In other words, I want to know at every theta value, when is this going to go through the origin? It's going to keep looping around, and I want to know what theta values does that occur. So we're going to set the equation equal to 0. Divide by 3, of course. Now, ask yourself this. Where does cosine equal 0? And of course, that would be at multiples of pi over 2. If you remember back to pre-calc, you had what was called a multiple angle trig equation. And what you would do is you take that 3 theta and set it equal to pi over 2 plus n pi. So pi over 2 plus any multiple of pi would give you solutions to this equation. And of course, we've got to get that theta by itself. So I'm going to divide by 3. So what we're saying is this curve will pass through the origin across the pole at odd multiples of pi over 6. And I want to be very clear about what's going on here. So every odd multiple of pi over 6, this curve is hitting the origin. If you were to start out at 0, so if you were to just start graphing this, say, in your calculator at theta equals 0, you would get a value of 3 here. So the first point you would see on the graph is right here. And then at pi over 6, it would immediately hit the origin. So one way to do this is to integrate from 0 to pi over 6. And think about if I integrated from 0 to pi over 6, what part of this petal would be swept out? It would just be the top half of the petal. So if I integrated from 0 to pi over 6, I would get half the petal, so I would just double it to get the area. Another way to do this is to think about, since this will hit at pi over 6, coming from the other direction it would have hit at negative pi over 6. So what they did in the book for this problem is they went ahead and just integrated this from negative pi over 6 to pi over 6. So let me show you that. So we've got 1/2 times the integral from negative pi over 6 to pi over 6 of r squared, which is 3 cosine 3 theta squared. So if we square that, brought the 9 to the front, we get this. And then remember that identity for cosine squared theta again. We get 1 plus cosine of 6 theta, you got double the angle, all over 2. Then, of course, doing a u substitution and integrating, we get this. Fundamental theorem of calculus, we get a value of 3 pi over 4. And what you'll notice is there are lots of ways to set up these problems. So, like I said, you could have gone from 0 to pi over 6 and just gotten the half of that petal and doubled it. And there's other ways to do this, but that was just the way that I came up with first. Let's try another one. Find the area of one small leaf of this function. So this isn't one of the ones that I gave you on the handout the other day. This one's a little bit different. So let's go ahead and graph the auxiliary sine curve that goes with it. Now, if you wanted to just go through and plot points on the polar curve, you could do so. But I want to show you what this looks like. If we were to graph this back like we did in pre-calc, the regular old sine curve, the period is 2 pi over 3. And in the PowerPoint the other day, I broke it down. I made this little chart. You do not have to do this. I just want you to see where I'm getting these values from. I use this thing called the quarter period, and I plug in these values of the quarter of the period into the function, and I get these corresponding r values. So here's what the function looks like. What I want you to take away from this, though, is that we're looking for the area of one small leaf. If you recall from the PowerPoint the other day, we said that if you have one small leaf on the inside of the function, let me show you a picture of it. One of these small leaves, that's going to be where this curve, the auxiliary curve here, is negative. So if I want to know when it's negative, I want the theta values for where this is negative. Think about what I'm going to do with that function. I'm looking for where the function has x-intercepts. So I'm going to set the equation equal to 0. And if you think about it in terms of polar, wherever this function equals 0, that's wherever we go through the pole. In all of these problems, if you're looking for where the function or where the polar graph hits the pole, you're going to set the equation equal to 0. If we add 1 divided by 2, we get sine 3 theta equals a half. This is another one of those multiple angle problems. Ask yourself, where in the unit circle does sine equal 1/2? And of course, that would be your pi over 6 and your 5 pi over 6 values. So I'm going to set 3 theta equal to pi over 6 plus 2n pi this time, and 5 pi over 6 plus 2n pi. You don't want to just do n pi because that would get me negative values for 1/2. We don't want that. We just want the positives. And then, of course, divide everything by 3. We get pi over 18 plus 2n pi over 3 and 5 pi over 18 plus 2n pi over 3. So think about in our graph, these x-intercepts are the first places where this function was equal to 0. So that would have been where n equaled 0. And so those theta values would be pi over 18 and 5 pi over 18. But to set up our integral, we're going to integrate from pi over 18 to 5 pi over 18 of the 1/2 r squared function. I'm going to skip the algebra this time and just tell you the answer is 0.1812 as a decimal. By the way, anytime you're doing integration in your calculator, go back to Cartesian mode. I don't think your calculator will integrate for you in polar. If it does, it's probably not what you're looking for. So just go back and put this in terms of x if you were doing this in the calculator. Okay, one last problem. Find the area of the region that's lying between the inner and the outer loops of the limacon. Let's make a sketch of it as the inner loop again. So the part in pink there is what we're looking for. So think about that last example. When is this going to have an inner loop? Well, if we were to look at the auxiliary curve, it would be the part that's underneath the x-axis. So again, I want to know the x-intercepts in order to figure out when this hits the pole. Think for a second, if you were to put in 0 for theta, you would get a value of 1. And that would be the first point right here on the graph if you were to plot it. And then somewhere between theta equals 0 and theta equals pi over 2, it's going to hit the pole here. So it would go from here to here. It's going to come back around and hit the pole again. So if we set our function equal to 0, we're looking for where sine theta equals 1/2. And again, that would be your multiples of pi over 6 and 5 pi over 6. All right, so what we're going to do here is I'm going to do actually two integrals. So the integral from pi over 6 to 5 pi over 6 is the inner loop. That represents the area of the inner loop. Now, the outer loop, if you look at this auxiliary curve, would be like if this is pi over 6 and this is 5 pi over 6, the outer loop would be what? From 5 pi over 6 to wherever the next x-intercept is. I'm going to say that again. If this is pi over 6, where I'm pointing to here, and this is 5 pi over 6, and that represents the inner loop, when do we start graphing the outer loop? It would go from 5 pi over 6 to whenever the next x-intercept is. Let's look at where that happens. 13 pi over 6. If we put in a value of n equals 1, the next value we would get here after 5 pi over 6, add 2 pi to the pi over 6, we would get 13 pi over 6. So let's see. The area of the inner loop is the integral from pi over 6 to 5 pi over 6. I'm just going to give you that value. The area of the outer loop, which includes that inner loop, is from 5 pi over 6 to 13 pi over 6. Remember, you got to think about sweeping. So if I'm integrating from 5 pi over 6 to 13 pi over 6, that's all of this area, including that inner loop. That gives me this value. So how do you think we're going to get the area of the pink region? We're going to subtract the area of the entire thing, including the inner loop, minus the inner loop. We get an area of pi plus 3 radical 3. Tomorrow in class and Friday in class, we're going to be practicing all of these area problems. So if it was a little unclear, don't worry about it. Just come in with questions, and we'll do plenty of practice tomorrow.